So, we talked about vector addition on Monday, okay, and we looked at just the addition of collinear vectors, and we looked at the addition of perpendicular vectors, okay, which are all pretty straightforward, simple math kind of things, okay. Component addition is what allows us to add vectors that are not collinear or perpendicular, okay, so these would be two angled vectors, or a straight vector and an angled vector. Okay, and what we'll be doing is finding out how far horizontally they go, how far vertically they go in total, and using that to figure out what the overall trip would look like. Okay, so it would set up something like this. Okay, so if I had a question that said, and you might want to write this example down. A person walks, let's say, 20 meters at 15 degrees north of east, then turns and walks, let's say, 8.0 meters at 40 degrees. No, that's a bad number. Hang on. I'm just trying to make this work in my head here. Let's say 15 meters at 40 degrees south of east. Okay, what is their total displacement? Okay, so what we do with vector component addition is exactly as it sounds. We resolve or break down all our vectors into their horizontal components and their vertical components. To do that, we need to use trigonometry. It's not really that hard, okay, in order to build right angle triangles for the two vectors we're given, as well as what we call our resultant vector. That would be the total at the end of everything, right? So we start out drawing our vector diagram, just like we learned how to do on Monday by drawing our vectors tail to head. Okay? Remembering that the length of the arrow represents the magnitude, and obviously we want to make it point in the direction we're told as best as possible. So our first vector is 20 meters long, 15 degrees north of east. So what I always do is I just draw a line along my reference, which is east. Okay, it says it's 15 degrees north of east. So what I do is I draw a line that's due east, a dotted line, and then I'm going to move 15 degrees north of that. All right, so this is 20 meters long, and this angle here is 15 degrees. Again, at least it's somewhat to scale. Right? I mean, that's maybe not exactly 15 degrees, but I'm sure it's close enough. When I walk along this 20-meter vector, I go somewhat east and somewhat north. Would you agree? Okay. So when I'm figuring out my components, what I'm doing is figuring out exactly how far east and how far north I go while walking along this 20-meter vector. In other words, I'm finding the horizontal, or x component, and the vertical, or y component, of that vector. Okay. Since I have the hypotenuse of this triangle and this angle, I can find the other two sides using trigonometry. Okay. That's what we call resolving the components, okay, or finding out what they are. So what trig function would I use if I want to find x? Or actually, let's say that a different way. In reference to this angle, is x opposite or adjacent? It's adjacent. Okay. I want to find x. I have the angle that's adjacent to it, and I have the length of the hypotenuse. Which trig function will help me find the adjacent side? Cos. Okay. So this is again where we have to remember our SOHCAHTOA. Okay. I can use cos because I am looking for the adjacent side. I have this angle and the hypotenuse. Right? So the cos of 15 degrees equals the adjacent side, which is x, divided by the hypotenuse, which is 20 meters. So I'm just going to put the 20 in there right now. Okay, how would I solve for x? Multiply both sides by 20. All right, so x is going to be the cos of 15 times 20. And remember, you want to be in degree mode. So always make sure you are. Okay, cos of 15 times 20. All right, so that side is 19.3185. I want to keep all those decimals in my calculator. I'm not going to write them all down because that takes too long, but okay, I'm going to keep them all in my calculator for further calculation later. All right, I also need to find y. Which trig function would I use to find y? It's opposite the angle that I have. I would use sine, okay? Because sine says, using this angle and the hypotenuse, find the opposite side, right? Opposite over hypotenuse, okay? So I'm going to go sine of 15 degrees times the hypotenuse, 20 meters, because I'm finding the other side now. That'll equal y. Okay, so y will equal 5.176 meters. Okay, that one's north, that one's east. Okay, so actually I'll put it in here, 5.176 meters. Okay, so I've just resolved that first vector of the two into its horizontal and vertical components. Okay, so I've just done kind of the first part. Now, the second vector says that they turn and walk 40 degrees south of east, 15 meters. So once again, my reference direction is east. And where do I want to draw the next vector? We always draw vectors, something to something. Tail to head, yeah. Okay, so I'm putting the tail of the second vector on the head of the first. So I'm going to draw my reference line that's east, and then I'm going to go 40 degrees south of that, 15 meters. That might be a little bit more than 40, but it'll work, okay? And that line maybe could be a little bit longer, but it'll work. Okay? As I walk along that 15-meter vector, I go somewhat south and somewhat east. And I need to figure out how far east and how far south I go while I'm walking the 15-meter vector. Okay? So if I want to find blue x this time, which trig function am I going to use? I have the hypotenuse and I have that angle there. Yep, I'm going to use cos again. Cos isn't always for x, it's just worked out that way for these two triangles, okay? But sometimes y can be the adjacent side, it just depends. Okay. So I've got a 40-degree angle here, okay, and I'm looking for x. So I'm going to go cos of 40 times the hypotenuse, which is 15. Okay, that'll give me the length of blue x. Okay, so that's 11.491 meters east. Okay, and then what trig function will I use to find y, which is now the opposite side? I have hypotenuse, and I'm looking for opposite sine. Okay, so y will be the sine of 40 times 15. 9.642. And that's south. Okay, so over the course of this trip, which consists of these two parts, I end up quite a ways east and a little ways south. Yeah. Okay. I mean, I go east and then I go east again, and then the first one I went north, and the second one I went south, but I went further south. I only went 5.176 meters north. Okay, but I went 9.642 meters south, so I definitely went further south, okay, over the whole trip, right? If I draw a line now that represents my total displacement, we would call that line the resultant. And I would draw it from my initial position, right here, to my final position, right there. Everybody all right with that? Okay. Now, I'm going to have to move this stuff down just a little bit. Oh. So this vector here goes somewhat south and somewhat east. Everybody okay with that? That's supposed to look like a right angle triangle. So this would be its vertical component. This would be its horizontal component, and this would be its angle, and it's going to represent the total displacement over the whole trip. Okay? Now, how can I figure out, let's just say, how far east it is? So I'm looking for green X. How can I find it? Exactly. Okay? I take the two X components and I add them. That's where the name vector component addition comes from. I'm going to add the X components together to find out my total X, and I'm going to add the two Y components together to get my total Y. Okay? I mean, if we look at this, right, I can take this line here and this line here, and they add up to the green line, do they not? Okay, so that's all I'm going to do. Right, I'm going to take their values, 19.319 and 11.491, and use them to figure out how big green X is. Okay, so green X is going to be red X plus blue X. So 19.391 plus 319. I'm going to use the actual numbers in my calculator. Okay. Right? This is where significant digits becomes a big deal. Never round off until the end. So even though it looks on the board like I've rounded off, I haven't. I'm going to use the full numbers from my calculator. Okay. All right. So I need that one. 19.31851653. Okay. Plus my 11.49. 0.66666. Oh, no, sorry, only 4 sixes. Ah, shoot, I lost one of the ones I need. Okay, 30.809 is going to be my X component, 30.809. Okay, meters east. So this side here is 30.8 meters. All right. How am I going to figure out Y, green Y? Can I do the same thing? Except that one of my Y's is negative, okay, or south. All right, so I'll take the two Y components. I'll have to calculate one of them over again, okay, but that's not a big deal. So I'm going to take this Y here, so 9.64. 5 plus, and then I'm just going to put in the calculation for that one there. So So that'll be the sine of 15 times 20.
Put times 2.
All right, so we got a total, oh, and I forgot to make one of them negative. That's better. Okay, so I end up 4.465 meters south after all of this. So my green y is negative 4.465. Okay, and all we did there was add the 5.16 to negative 9.642, okay, in order to get that one. All right, so now I have two sides of this triangle. Can I figure out my total displacement now? Okay, by doing, I do Pythagorean theorem. I've got the two sides of that triangle now. Okay, so I'm going to take the 30.8 squared plus 4.65 squared, and that'll give me D. So, and I lost it. Stupid. Okay, imagine I didn't lose it, because I can't go up and select it on this thing. It doesn't have that capability, even though your calculators do. Okay, so I'm going to do a very bad thing here. And I'm rounding off before I should. Okay, which is an especially big deal because I'm squaring that rounded number, but just pretend I didn't do that. Okay, plus my answer, which I'll keep all the points for. Okay, so I'm getting that my total displacement is 31.13 meters. Okay, so big D is the square root of green x plus green y squared. Okay, and then that one, that comes up to 31.13 meters. Okay, what else do I need to find? I've got how long D is, but now I need to know the angle, right? I need to know which direction it's going. So I'm going to find theta here. I can use any trig function I want at this point. All the numbers have been calculated by me. If I screwed up at some point, it's already too late. Okay, so you can use whatever your favorite trig function is now. Okay, in order to figure out what this angle is. You can use sine or cos or tan, it doesn't matter. My favorite's tan, so that's what I'm going to use. Okay, so I'm going to say that theta equals tan to the minus 1 of, for me, the opposite side for this angle is x, and the adjacent side is y. So 30.8 over 4.465. I messed something up in my calculation, I feel like. Nope, I didn't. Okay, good. Put that in the right way. Okay, so we're going to have our 30.809, which is the opposite side, divided by the adjacent side, 4.465. That'll give me my angle. Should be fairly large. So second tan of 30.809 over 4.465. Okay, so I'm getting 81 degrees here. Okay, so actually 82 degrees. I only have two significant figures in this question. So 82 degrees. Which way is that? Okay, so my angle arc is coming off of south. So it's something of south. Which way am I going from south? East. Okay, so this is going to be 82 degrees east of south. So our final answer to two significant figures is going to be 31 meters at 82 degrees east of south. Now, it is possible that you could have also drawn the triangle this way. I don't like to do it that way because then my diagram gets really confusing and busy looking. Okay, but if you did do it that way, that would be fine. Okay, you just would get a slightly different angle. You would get 8.3 degrees south of east. Either one of those would be correct in that situation because they're the same way. All right? Now, that's the first time you've probably seen one of those done. And I went fairly slow. Okay? Did it take us quite a while to do it? Okay. The only thing that gets you faster at this is repetition. So we're going to spend a fair amount of time working on vector addition problems so that we get faster at it. Okay? When you get good at this, you should be able to do a question like that in about 6 or 7 minutes. Okay? It took us longer than that. Okay? Probably closer to 12 or 13 minutes. Okay? And that's okay. Right? At first, it's not about how fast, it's about how well. All right, so basically, vector component addition is turn everything into a right angle triangle, find out how far horizontally, how far vertically, then put it back together, okay, to find your totals. All right, so if we go back to this here, okay, so what we're trying to do today or try to learn is what we just did, how to resolve a vector into its components, so finding x and finding y, okay, and then how to use those components to add vector quantities that are not collinear, which is what we did. All right, so if the magnitude and the direction of a vector are known, so if we knew how long A is, the blue line here is, and what angle it had, we would always be able to find its x component, AX, and its y component, AY. Okay? And we would do that obviously just using trigonometry. Okay? I would have to know how the magnitude of A, and I would have to know theta in order to do that. Okay, so we find the x and y components of a vector like that simply by using trigonometry, and I know that every one we've done so far, x has been cos, but that's not always going to be the case. Okay, I could have just as easily given you the triangle this way. Okay, so if I'd have drawn the triangle like this, instead of the way they did, okay, and given you this theta instead, sorry, this is, I did that backwards. This is y and this is x. Okay, x would now be the opposite side, so you would use sine for it, and you would use cos for y. So it all depends on the way the triangle is drawn. Okay, I just don't want you to memorize that. Oh, x is always cos because it's not. Okay. All right. So everybody okay with how that part works? Finding the x and y, right? We just figure out what side they are relative to the angle we're given. Okay, if it's touching the angle we're given, it's adjacent. If it's not, it's opposite. All right, so looking at this example here, if I've got a displacement vector that is 175 meters long, points 50 degrees relative to the x-axis, and the way they wrote that, it should probably say above the x-axis, because below is also relative, okay? So relative is not a great word to use there. I would have written this as 50 degrees above the positive x-axis. Okay? Remember, you probably learned this in math, right? When you have an xy plot, this is the positive y, this is the positive x, the negative y, and the negative x. Okay? Since this is pointing this way, it's 50 degrees above the positive x-axis. Okay? So that can be vectors that we get sometimes as well. All right, I want to find its x and y components. Okay? So right now, x, is it adjacent or opposite the 50-degree angle? It's adjacent, it's touching it. So what trig function am I going to use for x? If I have the hypotenuse, this is 175. Okay, and I have that angle 50 degrees. Which trig function will I use for x? I'm looking for adjacent. I have hypotenuse. Cos, exactly. Okay, so I'm going to use the cos of 50 degrees times 175. Okay, and that will get me x. So that's down here. Okay, and then y, it'll be sine because it's the opposite side. Okay, so this is what we just did. Okay, this is what we just did here. Okay, we had this small vector and then we had another vector. We found their horizontal and vertical parts. Okay, and then we added them together to get our total. Okay, so that's what we just completed there. That's what vector component addition is going to entail. Finding x and y for your vectors, adding the x's, adding the y's, getting your totals. All right. And we've already talked about that. Okay, so this is going to be our first example. Okay, so in this one, we've got two vectors, A and B. Okay, A is 145 meters, and it is 70 degrees above the horizontal. Okay, B is 105 meters and is 35 degrees below the horizontal. We want to find the magnitude and the direction of C using vector components. All right, now, a little bit of confusion about this drawing. They gave me this angle for A, and then drew A's triangle over here. That's kind of dumb, okay? I can't use this angle for this triangle, but I can use this one. How big is it? It's 20, right? Because they add up to 90. So this is a 20-degree angle right here, okay? And then I'm looking for Y and X. And then for this one here, I've got a 35-degree angle there. So A is 145 meters. Okay, and B is 105 meters. Okay, so what I want you to start off with is find AX and AY. Okay, start off with that. Have the diagram, draw the diagram, okay, and then find AX and AY. I'll give you a couple minutes to do that, and then I'll walk through it, and then we'll keep going from there. Okay, so let's have a look at calculating kind of the blue vector's components, all right? So if we're looking for blue x, or AX, okay, which trig function am I going to use? Is it opposite or adjacent the 20-degree angle? It's opposite, yeah, okay, it's on the far side. That means I'm going to use sine. Okay, so I'm going to use sine of 20 times 145. So here, prime example, right? X is not always cos. Okay, it's not always the adjacent side. This time it's the opposite. All right, so blue X will be okay, the sine of 20 times 145. All right, so that side is 49.593. You know what? I'm going to write all the decimals because I'll probably lose it again. 59292 meters, and that is east. Okay, blue Y. Well, Y has to be the adjacent side if X was opposite, so that'll be cos of 20 times 145. So cos of 20 times the hypotenuse. So 136.25543. And that is north. All right, so I found blue X and blue Y. Okay, how many people have already found BX? And okay, so let's go through that triangle then. I don't have a yellow marker, so I'm going to do it in green. Okay, so the X component for our second triangle, okay, is the adjacent side, so that'll be cos of 35 times the hypotenuse of that triangle, which is 105. Okay, so 86.010. And that is east. Okay, and then the Y component of that triangle is going to be the opposite side, so it'll be the sine of 35 times 105. So 60.2255. Okay, I always put the directions on when I'm finding the components so that later I remember which ones are negative and which ones are positive, okay? If you don't want to do that, that's up to you. All right, so now I've got blue X and blue Y, yellow X and yellow Y, and now I'm looking to find C. Okay, well, I can find C as long as I know CX and CY. Okay, how am I going to find CX? Okay, this total here, CX, is the result of me doing this and this, right? AX and BX. So what do I do with those two numbers since I know them? Add them together, okay? Vector component addition. There's a reason we call it that. I want to add the two X components together to get my total X component. They're both east, so I don't need to make either one of them negative. I just need to add them in there, right? So I'm going to have my 49.59292078, okay? Plus the 86 here, 86.0106.465. All right, so in total, we go 135 meters east, okay? And I'm going to keep all those decimals as well. So 135.603. Okay, and then for the Y's, one of them goes north, the other goes south. So one of them has to be negative. So it'll be the 136. And I'm just going to put minus, okay, our 60.22552582. All right, so my total Y is going to be 76.029 meters north. Okay, now that I have those two sides, can I find how big C is? What do you think? Yes, I can. Okay, use Pythagorean theorem, and I'll get C, which represents my total displacement. All right, so second function, square root of my answer squared plus the 135.6038854 squared. All right, so we're getting a total here of 155.46. Now this question has 3 significant digits, I believe, for everything, right? Yes, it does. Okay, so we're going to keep the 155. So yeah, 155 meters. Okay, and now I need to find its direction. I can use any trig function I want at this point. I know all 3 sides. I had to do equal amounts of calculating to get them all. Okay, I'm just going to use tan because it's my favorite. Okay, so tan to the minus 1, so theta will equal tan to the minus 1 of the opposite side for my angle, that's 76, divided by the adjacent side, 135.6. Obviously, I'm going to put all the decimals in my calculator when I do that calculation. Okay, so second tan of 76.02990.418 divided by 135.603.885. All right, so I'm getting 29.3 degrees for that angle. What direction is that? north of east, okay? My angle arc is touching east, and I'm going north of that. Okay, so my final answer here is going to be that my overall displacement is 155 meters at 55, sorry, not 55, at 29.3 degrees north of east. Okay, and I could also have the complementary angle there, which would be 60.7 degrees east of north, if I drew the triangle the other way, which none of us did because we all did that way. All right, takes us a little while. That's okay. Right now we're just getting started with it. We're new to it. Okay. On a test, like on a unit exam, I have never given a vector addition question that actually had two angled vectors because it just takes too long. Okay. So typically on a test, what you would see would be something like this. You would get one vector that's either vertical or horizontal, so you don't have to do any trig for it, right? You already know whatever it is, okay? And then like one angled. Okay, so you would already know how long this is, and it would be an x component because it's horizontal. You'd only have to find this x and that y, and then you would get your total triangle. Okay? It goes a lot faster, but still you get to demonstrate to me you can find vector components, you know what to do with them when you add them, okay, et cetera, et cetera. It takes about 2/3 of the time to do a question like that as it does to do the one we just did. All right, so this is just the nicely typewritten version of what we just did over on the last screen. Okay. All right. So this is a velocity vector. Does it change what I do if it asks me to find its x and y components? The only difference is the x and y components will not be in meters, they'll be in kilometers per hour. Okay, I still find x and y in exactly the same way. Okay, I would find x using sine or cos. Cos. It's adjacent to the 25-degree angle. Okay, and then I would use sine to find the other one. Okay, so to find x here, okay, I would go cos of 25 times 100. Okay, because it's 100 kilometers per hour. Okay, for the y component, sine of 25 times 100. Okay, and I would have them there. All that would change is at the end my units are going to be in kilometers per hour. So cos of 25 times 100. All right, so that side's 91 kilometers per hour. East, okay, and the other side 42 kilometers per hour north. Okay, so basically what that's saying is if you're traveling 100 kilometers per hour, 25 degrees north of east, that means that every hour you're going to go 91 kilometers east and 42 kilometers north. Okay, that's what we're saying when we do. All right, I want you guys to see if you can do question number 1 and question number 3. Don't worry about number 2 because it uses the rectangular coordinate system, which we no longer do. All right, so I'll give you a couple minutes on 1 and 3. They're just finding vector components, so they're pretty quick. Okay, let's have a look at number 1. So if you recall, when we first started talking about vector addition, I told you that the trickiest part is not the math, the trig, or any of that. The trickiest part is the picture. Okay, we have to make sure we draw the picture correctly, and I find that that's often where people mess up. And it's the first step. Unfortunately, everything after that then is kind of downhill. So, okay, if I'm looking at our first one here, drawing the picture is going to be a 15-kilometer long vector, 40 degrees east of north. So before I can even start drawing that 15-kilometer vector, I need to get the angle right. It's east of north. North then is my reference direction. So I draw a line that is due north, just a dotted line because it's going to act as my reference. And I'm going to go 40 degrees east of that. And then draw my 15-kilometer vector. Okay? That's how I make sure I get my vectors right each time. Okay? I draw the reference, which is always the second direction given to me. Okay? It's 40 degrees measured this direction from this direction. Okay? In this case, east from north. Right? So here's my 40-degree angle. Here's my 15 kilometers. This would be my y component. This would be my x component. Right? If I don't get that drawn right, then I might calculate the wrong side when they're asking me for the north component. Right? So the north component is the y component. I'm going to have to find that by using trig. Which function am I going to use? Cos. Okay? The y is adjacent to the 40-degree angle, and I have the hypotenuse. So y will be the cos of 40 degrees times 15 kilometers. Right? When we do that, we should get 11 kilometers north. Okay, that's our answer. Are you all right with that? Okay, how many people have done number 3? So for number 3, okay, same thing. Got to draw the diagram first. 37 degrees east of south. Okay, there's my reference line, due south. I'm going 37 degrees east of that. And it's 65 kilometers long. Here's y, here's x. Okay, my x will be east, my y will be south. It wants to know how far east it goes, so what am I looking for? X. Okay, x is opposite the 37-degree angle. So which trig function do I use? Sine. Okay, so we'll have sine of 37 times the hypotenuse, 65. That'll equal x, and that comes out to 39 kilometers east. Okay, is that making some sense to people? Right, so that's like the fundamental skill involved in vector component addition, being able to find the vector components. Okay, guys, here's the thing to know about all vector addition. It's all the same. You always follow the same steps. Okay, draw the diagram. Find the x's, find the y's, add the x's, add the y's, do Pythagoras, get the final angle of trig, and you're done. It's always the same steps. Picture, components, put them together, find the angle, done. Okay, it's always the same steps. All right? The only time it's going to be a little bit different is if they give you the result and then ask you to find one of the parts. Then you have to work backwards. But it's still the same steps, they're just in a slightly different order. All right, we're not going to do that one because it's... And we can't do that one. But we can do number 2. So I want you guys to try number 2. Okay? Vector component addition. I'll give you a few minutes and I'll draw the diagram. Okay? Then I'll give you a few more to get the math of it done. All right? So we got a soccer player who goes 15 meters at 15 degrees north of east, then 13 meters at 5 degrees west of north. Scale is important here. Make sure you have it drawn at least somewhat to scale. Okay, let's just look at what the diagram's going to look like for this one. So first they go 15 meters at 15 degrees north of east. So my reference is east. All right, and I'm going to go 15 degrees north of that. That's maybe a little low. Okay, and it's 15 meters long. Here's x. Here's y. My second vector is 13 meters, and it's 5 degrees west of north. Okay, so my reference direction is north this time. And maybe I need to move this whole thing down just a little bit so I don't run out of room. going to draw my reference line north, okay? And this 13-meter line is going to be just slightly shorter than my 15-meter line to preserve my scale. 5 degrees is obviously not much of an angle. So there's 13 meters, 5 degrees west of north. Here's y, here's x, which means my resultant, which in this case is my total displacement, is a line running from my initial position to my final position. Whoa, that's crooked. Okay, imagine it's straight. Right? You could draw this triangle the way I drew it, or you could draw it over top of the other stuff. It makes no difference which way you draw it. You'll just get the opposite angle that I get. It'll still be right. Okay, if you get the complementary angle to mine. I just like for mine to not be over top of anything else if I can help it. Okay, so this will be my total displacement. This will be my vector. Here's x, here's y. So your diagram should look something like that. Okay, what's your next step after the diagram? What do you need to calculate? Your components. Okay, so the next thing to calculate are your x and y components. Okay, that's the next thing. Okay, so when walking around, I'm seeing that pretty much everybody's got the diagram the right way, and those who didn't kind of realize where they went wrong, which is good. Okay, gonna quickly talk about one thing, and that is sign law. I noticed a few people were using that. I want to caution you in regards to sign law. Okay, first thing, the curriculum for Math 10 and the curriculum for Math 20 both state that you're supposed to solve things using simple trigonometric ratios. That's sine, cos, tan, SOHCAHTOA, not sine law. Okay. Second thing is, in my experience, very few people are able to actually use sine law correctly often enough to be acceptable. Third and most important reason I don't like sine law, it gets you the answer with zero understanding of how you arrive at it. Okay? We need to be able to analyze vectors. We need to be able to look at a trip and analyze it from a perspective of how far east, how far north, okay? What part of this represented what, and we can't do that with sine law. Sine law just spits out an answer, and if you do it right, great, it gets you the answer. If you do it wrong, you have virtually no work to get part marks for, because sine law you just plug in. Okay? And there's virtually nothing there for me to go, oh, okay, I see where they went wrong. They probably just punched that part in right, but the rest of their method is good. I can still give them 7 out of 8. Okay? If you did sine law, I've got a diagram I might be able to give you a mark for, and an answer I can give you nothing for and nothing else. Okay? So that's my caution. Our big concern is the lack of analysis that goes on using sine law. Okay? Sine law will get you the right answer. I won't argue that. If you know how to use it and you get the right answer every time, that's great. But when it comes time to analyze a trip, okay, or analyze a situation, sine law won't do that. Okay, we need to be able to analyze a trip from kind of start to finish. Okay, so our second step here is that we need to calculate all of our x's and all of our y's. Okay, so if I want to find the x component of my first vector, it is adjacent to my angle, my 15-degree angle. So I'll be using cos for that. Cos of 15 degrees times the hypotenuse, which is 15 meters. Okay, so we got cos 15 times 15, and so that side's 14.489 meters east. Okay, so I've got black x. Black y is the opposite side, so it'll be sine of 15 times 15. All right, so we got 3.882 north. All right, so we've got those two. Got to do the same thing for the red triangle. Okay, for the red triangle, the x component is actually the opposite side. Okay, it's opposite that 5-degree angle. So x will be the sine of 5 degrees times the hypotenuse, 13 meters. Okay, so sine of 5 times 13. All right, it's going to give me 1.133 meters. And that's, sorry, east, not north. And then our y component is the adjacent side, so cos of 5 times 13. Is 12.951 meters north. Okay, so there's all my x's and all my y's. Right? I'll give you a few more minutes to get the rest of it done. Now that you got all the x's and all the y's, you got to solve for the total displacement, blue d here, with its angle, blue theta. Okay, to do that, you're going to need blue x and blue y. Right? Okay, so our last couple of steps. Okay, our last couple of steps involve finding x and finding y. So finding blue x and blue y. Okay, so in order to find those, I've got to add my x's together and my y's together. Now, my x's don't go the same direction. My first x goes east, my second x goes west. So one of them has to be negative. All right, so in knowing that, okay, I'm going to take my 14.489 and I'm going to subtract from that, or add as a negative, 1.133. Okay, so we got our 14.48888 and 739 minus our 1.133024. 656. Okay. All right, so my total x is going to be 13.356 meters east. Okay, and then for y, that'll be, the two y's are both north, so I can add them together. So we'll have, oh, I lost one of them. Okay, so the 12.9 plus sine of 15, cos of 15. Okay, so we're looking at a total north component here of 27.439. Meters north. Okay, so now that I have those, now can I get my final displacement and its direction? Okay, so we got Pythagoras and one more trig calculation and we're done. Okay, so we'll do our Pythagorean theorem calculation. So we'll take our 13.3556273 squared plus our answer from the last calculation squared. All right, so our total displacements, we only have two significant figures here, 31 meters. Okay, and then to find the angle, again, you can use any trig function you want. I'm going to use tan, so I'm going to go second tan of 13.355867273, which is my opposite side, divided by 27.43941,847. Okay, and that's going to give me 26 degrees here. And which direction is that 26 degrees? It's touching which direction? North, and it's going east. This is 26 degrees east of north. If you got the complementary angle, then you got 64 degrees north of east. Okay, and that's fine as well. All right, everybody follow on that one? Okay, so we're going to be spending some time working on those, okay, but we'll keep working on them. All right, if you guys can, please give your desks a quick wipe down there, that'd be awesome.